Well, welcome to the final video of Unit 5C. In this video, we're going to consider circuits that involve both series and parallel resistors. So circuits where there's a part of the circuit that's in parallel and a part of the circuit that's in series. We're going to develop a way to solve, a strategy to solve problems involving combination circuits. Then we're going to end by looking at the way that capacitors behave in a circuit. So let's just jump right on into it. So let's begin by looking at a problem-solving strategy for resistor circuits. Now this applies whether there's light bulbs in the circuit or resistors, and we can even use this strategy as we work in with capacitors, okay? To prepare, you're going to start by drawing a circuit diagram and label all the known and unknown quantities. Often a circuit diagram is given for you, but if it's kind of complex, you might want to analyze that circuit diagram and redraw it so it makes a little more sense to you. And you definitely want to make sure that you assign resistors R1, R2, and so on to that circuit. Then we're going to analyze that circuit based on Kirchhoff's laws and the rules for series and parallel resistors. Step by step, we want to reduce the circuit to the smallest possible number of equivalent resistors. That's going to involve taking the circuit section by section, adding together resistors that are in series, and using the parallel rule for resistors that are in parallel. Oftentimes you'll want to redraw that circuit each step of the way. Then you want to determine the current through a potential difference across equivalent resistors. Once you have that equivalent resistance, then you can begin to solve the parts of the problem that you need. Then we can rebuild that circuit using the fact that the current is the same through all the resistors in series and the potential difference is the same across all parallel resistors. Two things to check your answers in working with circuits is to verify that the sum of the potential differences across series resistors matches the potential difference for the equivalent resistor, and verify that the sum of the currents through parallel resistors matches the current for the equivalent resistor. Alright, so to make sense of this strategy then, let's start just by looking at a basic combination circuit problem. Okay, so here we're given this group of resistors and we're asked what is the equivalent resistance of this group of resistors. So we're going to start by assigning labels to them, R1 through R4, and then we look for groupings where there are resistors that are parallel together and resistors that are series together. Right here we have these two, R3 and R4, are in parallel with each other. We know that they're in parallel because regardless of which way that the current would flow through this circuit, it's going to come to a point where it goes into a junction. That anything after that junction, any circuit elements after that junction, are in parallel with each other. So let's start by finding an equivalent resistance for just R3 and R4. So we apply the parallel resistor rule for this, and we get an equivalent resistance of R34 of 30 ohms. What this means is we could effectively replace R3 and R4 with a single 30 ohm resistor, and it would have the same effect on that circuit. And we can actually redraw this circuit to look like this, where we've got R1 and R2 still in place, and we've replaced R3 and R4 with a single resistor, R34. Now when we look at this, we see that there, regardless of which way the current comes, either from the top or the bottom, there's a junction there where R2 and R1 and R34 are in parallel with each other. R1 and R34 are in series with each other. So what we're going to do is apply the series rule to R1 and R34 and come up with an equivalent resistance, R134. Because they're in series with each other, we simply add their resistances and we come up with an equivalent resistance, R134, of 40 ohms. Then we're going to redraw the circuit to look like this, where we've got R134 and R2 in parallel with each other. So all we need to do here is apply the parallel rule to this equivalent circuit, and we're going to get a total resistance of 24 ohms. So this whole original circuit is really just a 24 ohm resistor in effect. Now it can seem kind of tedious a little bit to have to go through and redraw the circuit, but when we get more and more complex circuits involved in problem solving, then it's going to be a strategy that you can use that's really, really effective to make sense of what's going on in these circuits. Now, two special cases to keep in mind that when we're talking about reducing circuits are the equivalent resistances of two identical resistors. When resistors are identical, it doesn't have to just be two, it could be 4, 10, whatever. If they're all identical, if they're in series, you can deal with them this way. And if they're in parallel, it's just the resistance divided by the number of resistors. But this only works when those resistors are of equal resistances. In this problem up here, that wouldn't have worked because the resistors are different resistances. All right, let's take a look at another example. Okay, so here we're asked to find the current and potential difference across each of these 4 resistors in this circuit. So we're going to start by assigning labels to each of those resistors, R1 through R4, and then break down the circuit step by step into one with a single resistor. And we can do this in 3 steps. And you always want to kind of start with the most isolated part of the circuit, which in this case is going to be these 2 parallel resistors, R3 and R2. Focusing on just those 2 resistors, we end up with an equivalent resistance for R23 of 240 ohms. So we can redraw the circuit to look like this here, where we've got R1, R23, and R4. From this redrawn circuit then, we can see that the R2 and R3, R23 and R4 are in series with each other. So we apply the series rule to those 2 resistors to get an equivalent resistance of 800 ohms for those 2 resistors. Redrawing the circuit again, we see that the R1 and R234 are in parallel with one another, and so then we will apply the parallel rule to those 2 resistors to get an equivalent resistance for the entire circuit. We do so and we get a total resistance then for the whole circuit of 400 ohms. Okay? So that's my total resistance for the entire circuit together. Okay? We want to then, since we're asked about the current and potential difference across each of the 4 resistors, we need to figure out first what the total current is for the whole circuit. We're going to do that by applying Ohm's law. The potential difference for this whole circuit is 12 volts. We're looking for the total current, and so we're going to use that total resistance. So we end up with a total current of 0.03 amps. Once we have this, we have our total potential difference, we have our total resistance, and now we have our total current. And we can begin to look at individual resistors in this circuit. We then apply the circuit rules and are able to figure out what we need to for each individual resistor. To do this, we kind of have to work backwards from where we started with finding the total resistance of the circuit. When we look at this here, we've got R1 and R234. So that's R1 here and the equivalent resistance of R234, both of which we found to be 800 ohms. And they're effectively in parallel with each other. Now we know from the parallel rules that the voltage drop is the same across each leg and the total current is the sum. So what we can do is apply Ohm's law to figure out the current through this equivalent section. To do that, since they're both 800 ohms, okay, we can just use the 800 ohms for one of those resistors and get a current then of 0.015 amps. And this will be the current then across resistor 1, 0.015 amps. And it'll be the current across the equivalent of resistor 234. The voltage drop across resistor 1 will be the full 12 volts. So then now what we have to do is take another step back to the circuit equivalent that was right before this one. Now, because in this equivalent circuit, R23 and R4 were in series, we have to look at the series rules for the voltage drop. For the current, okay, the current is going to be the same through this. Resistors in series, the same current. So the 0.015 amps that goes through R1 also goes through R234. R23 and R4 are in series, so it's 0.015 amps go through here. However, voltage drops add up for resistors in series. So while there's 12 volts here, there's not going to be 12 volt voltage drop through these two resistors. We have to figure them out separately. So we'll start by looking at the voltage drop through resistor 2,3, where we know that the current is going to be the 0.015 amps, and the resistance of R23, which we figured out in the previous steps of this, was 240 ohms. This gives us then a voltage drop across resistor 2,3 of 3.6 volts. We then follow the same procedure to find the voltage drop across resistor 4, and we end up with 8.4 volts. Because we know that these are in series also, right? We know that series voltage drops add up. We know the total voltage drop through there must equal 12 volts. The 3.6 and the 8.4 equal 12 volts. Our final part of this then is to be able to figure out the current and voltage through R2 and R3 individually in this parallel section here. Because this parallel section is equivalent to R23, the voltage drop across R23 is 3.6 volts. So we know that the voltage drop across R2 and R3 individually will also be 3.6 volts because that's the parallel rule for voltage drops. The current, however, adds up for those resistors in parallel. But we know that the total current through this section will be the 0.015 amps. And so the current through each individual resistor, R2 and R3, needs to add up to 0.015 amps. So when we apply Ohm's law to find the current through resistor 2, we're going to use the resistance of resistor 2, the 3.6 volts, because we know that that's the resistance through that parallel section, our V23, and we end up with a current then of 0.009 amps. Following the same procedure then to find the current through resistor 3, we end up with 0.006 amps, which adds up to the 0.015 amps that we expected. Okay, so that's figuring out combination circuits, finding voltage drops and currents and resistances through combination circuits. I suspect that you probably will have to rewind and go through that a few times before you kind of understand the logic behind them. We'll have plenty of practice on these in class. We'll see you then.